Okay, so in this one, this show and tell, we open the CTL model, the CTL state variable. So this is built by a student, myself and David Vickers, and it's kind of symptomatic of a whole, or emblematic of a whole class of models that David Vickers and I built. David's at Alberta Health Services, but he actually submitted a CV. I don't know if you remember. Yeah. So he's an extraordinary guy. He's a microbiologist by training and statistician, but also did a tremendous amount of modeling for us, and got his PhD under me. And he was very interested in immunoepi models that would combine a representation of immune dynamics within a person with transmission dynamics in a population. So through the skin, some things inside a person, some things outside. And he used this lens for a couple bugs, including chlamydia, which was the subject of his doctoral dissertation, and where he had several models published, and flu. That was work done with Benny Sahai, unfortunately a late colleague from CADM National Labs, who was very active in the mathematical modeling community in Canada. And then we did it as well for some infections that were characterized in a book on viral dynamics by Nowak and May, I think it was. And this was one of our earliest models, which just showed a proof of concept. So here within a person, we have some stock. This is a differential equation model, some stock of free virions. And virions are produced by lysing of cells that are infected, and they're cleared at a certain rate. And
what are the clouds though?
Oh, these clouds just mean it's outside the scope of the model. So when virions get produced, we're not really interested where they come from. That, they're formed. We're not interested in simulating them coming from another compartment and going to this compartment. Rather, they just they come from somewhere. We're not simulating. It's not in the scope of the model, and they're coming here. And then after they are cleared from the body, we don't really simulate where the virions go. They're destroyed, and so we don't simulate it. But notably, virions can come from neighbors. So I can get exposed. My viral population can grow slightly, and it's a very small effect, according to this parameter omega, based on the influence of others. It's a very small amount of virions that come in, but it's enough to set off a viral multiplication chain. And then we have uninfected cells and infected cells. In our work with Benny Sahai, this was cells in the esophagus. So it's esophageal cells for flu. And ladies and gentlemen, then we had cell death from this infected cell state. Okay, here within this model, we had infection taking place of cells. But not only that, as that infection took place, it stimulated the production of cell-mediated immunity. So that's the Z stock here. And Z represents activated T cells, basically. And in the model with Benny and some other models that we worked on, you had different stages of activation. So you had precursor T cells and activated ones. But basically cells build up, and when they're built up, stimulated by the occurrence of infectious cells, and when they're built up, they kill off infectious cells through lysis. They destroy the infected cells, and therefore stop them from propagating. Okay, so within this model, I'd like to simulate things. So if we go to if we go to high viral threshold here, this is a scenario here. One of the things we'll see is we'll see a population of people, and one of these people is going to start infected, and they're going to grow infected. And just to give you a description, I think the width of this depends on their level of immune activation and the redness on their level of viral load. Okay, so they are starting to recover right now, but they've exposed others in the network right around them, And so these people start to get sick. You'll notice that they get high levels of viral load first. It becomes very red. But as their immune system responds, as you see from the width of the cell, it starts to overcome the high levels of infected cells and free virions, and so they recover. Now, down at the level of an individual person, therefore, what we're seeing is dynamics that are characterized by the stock and flow. Here's their viral levels, for example, of a given person. We see this kind of pulsed episodes associated with this. So this model is fairly fairly stylized. It was based on a published model from immunological work that came out of Nowak and May's group, but it was a stylized depiction. In other work that we did, it was highly based on laboratory experiments, okay, including Benny's excellent work at Chatham National Labs, but also including work done by those researching chlamydia in the lab. Okay, so let me just highlight one other thing for you, though. I'm going to stop this model, and then I'm going to go down to this one with low fatal threshold, and we're going to let's go to medium fatal viral threshold. Here, ladies and gentlemen, we're going to have a threshold in place that's quite modest for how sick someone could get. And if they get above that level of viral load, they'll die, okay? In which case they're removed from the network. And so think of this as flu in a long-term care facility or in a hospital with very weak patients. And elderly patients are at risk due to dehydration, other factors of death from flu. And so some of those sickest individuals are removed. You can characterize that. How do we do that? Well, this is a hybrid model, ladies and gentlemen. So here we have persons, and within persons we have stocks and flows. And importantly, this is a key point, this characterizes their continuous dynamics. Their dynamics with respect to these essentially continuous quantities, free viral load, free virions, level of immune activation, and number of infected cells. But you can also characterize for the same individual state charts about whether they're living or dead. And this state chart transition is based on a condition, okay? And this condition basically asks, is their viral load above a certain threshold? If so, they are removed from the population. Okay, so here we have a hybrid model, continuous dynamics caught or captured via stocks and flows within a person, much as you might capture weight dynamics, metabolic change, body compartments, would be another prime example, or risk perception. And here, the dynamics associated with that are more discrete in character, living or death, that's captured in a discrete fashion. Okay, a discrete fashion with state charts and with conditional transitions on state charts. Okay, so this is a hybrid model that combines those two. So I'm gonna close that out. We're going to look at one or two other hybrid models. I'd like to look at a model that's called the budding hybrid SD-ABM model. Okay? Budding hybrid SD-ABM.